Hi, I'm Fabian, and I present a new pathway to approximate energy expenditure and recovery of an athlete. Our work can be summarized in two contributions, which on one hand is a generalized model to approximate energy expenditure and recovery, and on the other hand is an evolutionary computation approach to fit this generalized model to individual athletes. As you can see on this slide, we focus on the area of cycling, and improved performance model in the area of cycling can optimize pacing schemes, can help to improve training schedules, or give a new in-depth perspective on performance analysis. Our generalized model is depicted on the bottom left, and this generalized model is based on some approximations of metabolic responses to exercise that were published by Morton. Morton published this three-component hydraulic model, and we generalized each of these components further. We generalized the left component as the aerobic component, the middle component as the anaerobic fast component, and the right component as the anaerobic slow component. How this all plays out together, you can see it in this animation. The three components are an abstraction of human metabolism, and each component is a tank that contains liquid. Liquid flow within the system of tanks represents energy dynamics. A tap is attached to the bottom of A and F, and you can open and close this tap according to energy demand. As you can see here in this animation, this tap is opened now, and energy is utilized from A and F, A and S, and AE. AE is assumed to be infinitely big, but A and F and A and S are limited. Such a system allows to model energy expenditure and recovery in a new perspective that allows to address current issues in performance modeling. But, however, the system is not validated on individual athletes because these tank capacities require in-depth knowledge of metabolic capacities. Morton originally defined tank sizes and positions according to metabolic measures, which cannot be obtained in the required precision or quantity. We therefore redefined these components as AE, ANF, and ANS to remove their ties to concrete metabolic measures and to allow to fit them with an optimization approach. We proposed evolutionary computation as the optimization approach to fit such a system of tanks to an individual athlete. To do so, we defined two objectives, one for energy expenditure and one for energy recovery. For both objectives, the three-component hydraulic model simulates exercise tests that were actually conducted on real athletes to determine energy expenditure and recovery dynamics, and then the differences of simulation and actually observed results are compared. As you can see here on the y-axis, recovery normalized root mean squared error measures are here, and expenditure normalized root mean squared error measures are on the x-axis. An example Pareto font is displayed, and the best solution is the one that has the smallest or closest distance to 0.00. To find this Pareto font and to find the best solution, we use the library PyCmo, and we use the multi-objective evolutionary algorithm with decomposition as implemented by PyCmo and combine it with the asynchronous islands functionality. Results closely resemble expected responses. As you can see in the top graph, the assumed hyperbolic relationship between exercise intensity and time to exhaustion, how it is assumed in performance and exercise sciences, is closely matched by 10 individually fitted hydraulic models. Only in the high intensities, there are some slight deviations in predicted time to exhaustions. These 10 fitted hydraulic models at the same time also match expected recovery ratios quite well. Here in this graph, you see three different observed recovery ratios as they were published by Kane and others for two different overall conditions. You can see that these 10 individually fitted hydraulic models recreate or match these reported mean values quite well. Overall, this proof of concept is a very high motivation to investigate the hydraulic perspective on performance modeling further, and also to optimize and further investigate evolutionary computation as an approach to fit such systems of tanks to individual athletes. Thank you very much. Please have a look at our paper if you want to know more, or visit us at the poster. Thank you.